Good afternoon, I am Maha Moussa and my teammates are Farag, Noha Mohamed and Amro Albegirmy. Today we'll be presenting to you our thesis project. This is our table of contents. Our project idea is to implement a brain-computer interface that classifies EEG signals into their corresponding motor commands. We wanted to help people suffering from paralysis live a more autonomous life. Brain-computer interface is one of the widely used technologies for such purpose. The EEG signals are translated into commands that can be used to control devices such as wheelchairs. We aim to contribute to the research done in the field of motor imagery classification through EEG signals. The outcome of our thesis is a research paper that documents our major findings. The EEGNet dataset is one of the largest and most widely used datasets in our area of research. We chose the dataset with the largest number of subjects to make our model more generic and account for the variations in the EEG signals produced by different people. The data was collected using 64 electrodes and sampled at 160 Hz. EEG signals of 109 subjects were recorded. Each subject performed multiple tasks, including resting and moving either the right fist, left fist, both fists, or both feet. In total, the dataset has approximately 1,500 EEG recordings, each belonging to one of the tasks I just mentioned. The dataset is composed of signals obtained when the subject imagines performing a task or actually moves to perform the task. So each one of the subjects was asked to perform 14 trials, and each trial lasted for 125 seconds. 2 out of the 14 are based runs and are used to identify the baseline or the resting signal. The odd number trials are actual movements of left or right fists or both feet, while the even number trials are imagined movements. For our research, we're interested in the motor imagery runs. The rest state is given the label T0, while labels T1 and T2 can actually be divided into 2 other labels based on which run it is. So T1 would just indicate left fist, T2 would indicate right fist, T3 would indicate both fists, and T4 would indicate both feet.
It was found in literature that authors would develop their models such that they target either 2 or 4 classes, as well as different subjects, such as it trains on single subject or train on all the dataset, all of the 100 subjects, to create a global model. The single subject training would require retraining for every new subject. We have taken a different set of approaches for training the dataset. This is a summary for approaches that were taken. Let's start with our first approach, which is the Cascade CNN LSTM model. The signal, which is in the form of 64 channels, is converted to a 2D mesh by placing each signal in its spatial location, just as the electrodes are located on the subject's brain. Then the signal is sliced to windows and inserted to convolution layers with doubling depths 32, 64, and 128. Then the outputs from CNNs are put on 2 LSTM layers to extract temporal features. Then the output of the last LSTM unit is inserted to a softmax layer to make a prediction. The accuracy of this model was found to be only 56.5%. Our second approach was using 2 simple ideas, which are the shallow net and deep net models. The shallow net architecture is quite simple. It just has 2 convolution layers, 1 batch and 1 pooling layer. This architecture was found in literature, but it was used to classify 2 classes only and for multiple subjects. The binary classification accuracy was 82%. The deep net has a deep architecture which starts with a convolution layer, followed by a repeated convolution, batch normalization, and pooling layers, repeated 4 times. The accuracy for binary classification was about 71%, which was surprisingly less than the shallow net. So we thought about combining the main concepts of approach 1 and approach 2 by converting the input to a 2D mesh and using 3D convolution. Surprisingly, this approach had a very good impact on shallow net, where the accuracy went up to 78%, but the DeepNet improved to 59% only. We noticed from training behavior of DeepNet that it overfits on the given dataset, which could be the reason.
Now I will discuss our third approach, which is another CNN model. EEGNet is another approach that we followed. This model is considered to be one of the current state-of-the-art implementations for EEG signal classification. The model is a CNN model with a basic CNN architecture, including batch normalization and max pooling, which can be seen in the architecture diagram above. This model was not created to solve a single classification problem. However, it was an attempt at creating a general model that can train any EEG-based classification problem. It showed promising results on some sample data that was used by the creators of the model to show the model's performance. When we tried to train the model on our dataset, we reached an accuracy of 64.7% when we trained it on 100 subjects and all 64 channels. One of the reasons that EEGNet underperformed was because the model was not complex enough to handle the complexity of EEG signals. However, due to its lower complexity, EEGNet has a higher speed than many of the models in our research. This brings me to the next model we tried, which is EEGNet Fusion. In order to solve the problems of EEGNet, EEGNet Fusion was introduced. EEGNet Fusion consisted of 3 branches, where each branch is given the same input. Every one of the 3 branches had the same structure as the EEGNet model, but with different kernel sizes and number of filters at the convolutional layers. After passing through the 3 branches, the weights are then merged at the fusion layer, and the output of that layer is then passed to the softmax classification layer. EEGNet Fusion outperformed EEGNet in terms of accuracy. It reached an accuracy of 67% on 100 subjects and all 64 electrodes. However, EEGNet Fusion is almost 3 times slower than EEGNet due to its higher complexity. We also made some changes to the inputs of both models in order to increase their performances. We changed the input to the network to be in the form of a 2D mesh in order to account for spatial properties of EEG signals. The results mentioned previously are the results of both models after applying a 2D mesh.
The next approach I'll be discussing is a recurrent convolutional neural network whose input are images made out of the EEG signals. The EEG signals undergo some pre-processing. They're split into 7 windows as information can be extracted from the temporal change in the brain activity. Then, to preserve the spatial and spectral structure of the signal, each window is converted into an image. The images are then fed to the model. The architecture of the model is shown in the diagram. It's composed of 7 parallel CNNs followed by an LSTM layer and a 1D convolutional layer. Unlike our previous approaches, this model's classification accuracy is per subject. By training on 40 subjects, the majority of accuracies we got were in the range of 92% to 95%. A few subjects produced accuracies in the 70s and 80s range. In addition, some subjects produced accuracies of about 45%. However, we found out from research papers that the data of these subjects were corrupt, therefore we removed them from our dataset.
So now that we mentioned all the approaches we attempted, let me introduce our best performing model, which uses scouting with a CNN-based architecture. While working on almost all of the previous models, we saw that overfitting was a persistent problem that wasn't easy to overcome. We then realized that the reason that overfitting was a big problem was due to the number of electrodes we used while training. We were initially using all 64 electrodes to train the signal. These 64 electrodes are placed on many different areas of the brain that correspond to different human functions and emotions, which can be seen from the image on the left. We realized that our models were always overfitting because we used all the electrodes from the signal, which contained signals from different parts of the brain that did not contribute to the classification task at hand, which was classifying activities related to motor imagery or movements. Therefore, we decided to only use the electrodes that contain the signals related to motor movements or imagery. This is how we were introduced to the process of scouting. Scouting is the process of picking electrodes that are located in a specific part of the brain. Scouting helped us identify which electrodes held the information we needed to train our models. The image to the right shows an example of the part of the brain that is active during motor imagery tasks. The architecture of our model can be seen in the image above. Once we identified the electrodes we needed to classify our data, our model's performance was significantly improved, and the problems we faced with overfitting were reduced, making it much easier to find a model that can perform the classification task at hand with very high accuracies, while still being able to generalize well and classify EEG signals obtained from any random subject. Through our research, we discovered that many state-of-the-art solutions used a CNN-centered approach when creating their models. And after reviewing the available literature and understanding our data, we realized that the best approach would be to use a CNN-based classifier. We experimented with many different models, and the best accuracies were produced by the architecture shown in the image, which is just a simple CNN model.
Now I'll be discussing our results and experiments. Now I'll be discussing the scouting testing to get valid results. The dataset was split into a 70% training set and 30% for testing and validation. The dataset is then split into two scouting sections, L1 and R1, each containing 4 electrodes located around the motor cortex, as none of the electrodes on the Epoch X headset, the one we were using, are located over the motor cortex. Therefore, you can see that the left electrodes that we use are AF3, F3, F7, and FC5, and the right electrodes are AF4, F4, F8, and FC6. To reach the decision of using these electrodes, multiple experiments were conducted to test scouting by trying different sets of electrodes, which will be discussed next. At first, we tested with 14 electrodes as shown in the image on the left, and the resulting accuracy was 86.40%. Here, no scouting was implemented as we've used all our electrodes. Then we've experimented with 7 electrodes, and their locations are as shown on the right, and the resulting accuracy was 82.14%. Here you can see the problem with 14 electrodes, that we are still using electrodes far away from the motor cortex and have no use to us in motor detection, and with the 7 electrodes it's the same. The third experiment was with 4 electrodes only on each side, surrounding the motor cortex area as shown on the left, and the resulting accuracy was 90.48%. And our last experiment was using 2 electrodes on each side, resulting with the accuracy to drop to 44.04% as shown in the image on the right. And here, 2 electrodes were just not enough to detect the tasks, as they were also not on the motor cortex, just surrounding it. As you can see here, scouting with 4 electrodes had the highest accuracy, as opposed to also no scouting at all, which is the 14 electrodes. So with scouting, we had an increase in accuracy with about 4%. Also, the 7 and 14 electrodes, as said before, didn't do so well because they were including all the electrodes just on one side, which defies the purpose of trying to limit our electrodes to only electrodes on or around the motor cortex, and 2 electrodes were just not enough. Now, after figuring out the scouts, we tested our model to see accuracy per task with the EEG signals, and the results accuracies on the test set for each class range from 85% to 95%, with task 1 having an accuracy of 85.25%, task 2 having an accuracy of 95.38%, task 3 having an accuracy of 93.01%, and task 4 with an accuracy of 87.7%. So as you can see here, our model is able to detect the tasks really well. There are many works that perform the same motor imagery tasks on the same dataset with each other in order to verify the effectiveness of our model. A summary of the results is shown. As you can see in the table, based on the papers we're comparing our works to, our model performs the best between the models. All of the mentioned works use 64 electrodes for classification. By decreasing the number of electrodes to only 4, we were able to decrease the data dimensions and increase the model's performance. Therefore, overall, the proposed model with scouting has an apparent great performance and has high accuracies in all tasks.
To compare all our approaches, the Cascade CNN LSTM, DeepNet, and EEGNet Fusion are the largest models. Approach 1 had no pre-processing at all except for Z-normalization, while approach 2 and 3 only used filters such as bandpass and notch filters. Approach 5 demanded heavy pre-processing. This led us to prediction speed being fastest for shallow net but very slow for EEGNet Fusion and imaging approaches. Approach for pre-processing time was reported last time to be complex. However, it was found that in testing or predicting, the values calculated in training are used immediately, and it's not recalculated again. It's worth noting as well that pre-processing had more impact on accuracy than model architecture.
And now I will demo our desktop application. Okay, this is our desktop application. So it's meant to act like a simulation, and the output here is the probability that this event belongs to a certain class. So for the next event, this event most likely belongs to task 3. This event most likely belongs to task 2. This event most likely belongs to task 2, and so on. If we look at the percentage at the top, this is our prediction of this EDF file, but this accuracy is only available now because we have the labels from the dataset, and it's here for demo purposes. And then if we scroll to the bottom, here we have a summary of each task, and this is meant to guide the user to tell them the probability of the accuracy of each task and how likely is each task correct. So for example, here task 1, the accuracy is 85.25, task 2 it's 95%, task 3 it's 93, and task 4 is 87.69.
As we mentioned in our previous presentation, the headset arrived really late, so we only use it to read signals. If we had more time, we would have been able to gather more data and use it to fine-tune the model according to the headset data, then use it for testing. However, we made sure that the electrodes we chose for scouting in the model are the ones available in the headset. The following video is a demonstration of reading the signals in real time. So I started out by being at rest for a couple of seconds. And then I started clenching my teeth, and you can see how that greatly affected the amplitude of the EEG signal. And now I'm back to rest. Now I started to blink rapidly, and that also appears in the EEG signal. Now I stopped. And now I started smiling, and that appears in the EEG signal also. Now back to rest. And now the peaks that appear in the EEG signal even after I stopped moving or smiling are as a result of me blinking. Our thesis outcome is research. We're done with writing the research paper, and this is a screenshot of the first page. Our advisor, Dr. Mohamed Moustafa, has suggested some conferences through which we can publish our paper. One of these is the 13th International Conference on Neural Computation Theory and Applications. We plan on submitting our paper to this conference as it will be completely online and we wouldn't have to travel because of the pandemic.
We have learned a lot throughout our senior project, not only in the literature related to our topic, EEG application, but also in deep learning concepts, mathematics, as well as flavors of a single technique. For example, we found ourselves in need to understand the difference between convolution layer, separable convolution layer, and depth-wise convolution layer. We also learned that understanding and pre-processing data is probably one of the most important tasks in deep learning projects. We got stuck for quite some time, and it took no time for our advisor to point out that some more attention should be given to the data, and it was indeed the key to most of our problems. We are proud to have been able to create a state-of-the-art model that's able to overpass models found in the literature, as well as to be able to publish our first research paper. We were so eager to see our model working live on the headset, but we are able to imagine how much of help EEG motor classification can help in wide variety of medical application, making us glad that we are able to contribute to the community, and therefore we will be making our code available publicly on GitHub. For future work, we recommend experiments that use LSTM with scouting. We also recommend to attempt different scouts if more or different electrodes are used or different headset is available. It's also possible to extract a small dataset from emotive headset and retrain with the EEGNet dataset, so this will help in testing the model with the headset. Thank you very much.